guys, hello. We're coming to you today. Mr. Fickes is recording, and I'm here to help you to review for your plate tectonics test that's coming up. And this PowerPoint presentation pretty much goes along with your review sheet, so you might use it in a way to help you with it. But here's where we started our plate tectonics unit, with background about Earth's layers. And there are 3 layers: the crust, the mantle, and the core, when we look at the layers based on composition or what they're made of. And what I want to focus on most with you would be the differences between continental and oceanic crust. The continental crust is thicker, less dense, because it's made of silicate minerals. Silica and magma is a key concept there. And then oceanic crust is thinner, more dense, because it's made of native elements, not silicate minerals. Then we worked out on some other layers based on temperature and pressure differences. And those layers are the lithosphere, stenosphere, mesosphere, outer core, inner core. The 2 most important ones for our unit would be here, that the solid lithosphere is also known as a tectonic plate. Different sections of lithosphere, almost like saying crust, are tectonic plates that float on the jelly like a stenosphere. Now, this concept of pressure and temperature, the closer you get to the inner core, you are under more temperature, higher temperature, but also under more pressure. When pressure wins, it stays a solid. When the pressure changes more dominant, but when the temperature increases more dominant, it stays a liquid. So pressure wants to hold it into a solid, and an increase in temperature wants to make it a liquid, so it's a battle. The jelly like a stenosphere that tectonic plates float on, that layer is like a tie between the temperature and pressure increase. Now I have a couple of slides in here to compare these 2 systems side by side. You can see crust, mantle, core over here, but then on this side you have lithosphere, which is the same as saying a tectonic plate floating on the jelly like a stenosphere. So the stenosphere would really be mantle material. Okay, now the reason I included this one is to show some differences between continental and oceanic crust. Here you can see oceanic crust. When you see that, you should be thinking, Ms. Fickes, that oceanic crust is very thin, where the continental crust is very thick. Okay, so after that background of Earth's layers, we move to this concept, that the continents haven't always been where they currently are, and that the fossil evidence is one thing that tells us there used to be a Pangea, which means all land that is split into present day. Well, here's the guy we know and love, Alfred Wegener. And you know, this poor guy had reasons in the early 1900s to think that there was a Pangea. Fossils were in weird places. For example, tropical fossils in Greenland, glacial grooves matching on separate continents, and the perfect fit of the continents. They look like a puzzle. But here was the issue. And when I say here's the issue, you should be thinking, Alfred couldn't explain how. And he couldn't explain how the continents split at all. They really laughed at him, and during his day, he was not a famous scientist. But now they know the how, and that's called seafloor spreading. Now notice here the plates pulling away. This is at the mid-ocean ridge through the Atlantic Ocean. That magma comes out, cools into new crust, pushes the old crust away, and moves the continents. It's the push, push, push to move the continents. But you probably remember a day that had a lava lamp, and the lava lamp showed the sinking and rising, like what's going on in the jelly like a stenosphere. And so these currents of convection, the rising and sinking due to temperature differences, it's kind of like wheels that keep the plates moving. So seafloor spreading plus convection really explains how. Now we have a new name for this old idea. And this was something that was tough on our plate tectonics quiz. That plate tectonics is the combination of 2 ideas. Continental drift, which explains what happened. And when we say what happened, that's like saying, oh, Pangea split. But seafloor spreading is how. And that's all this business at the mid-ocean ridge, with the magma coming out, cooling into new crust, and pushing the old crust away. And you can see here, from this slide, I wanted to show again that this part right here, lithosphere, is like saying a tectonic plate, and it floats on the jelly like a stenosphere. All right, here it is. When you see this map, your first thought might be, oh, that's Pangea. Actually not true. When you look at the continents are in their modern day locations. They're modern day locations. So, this isn't a map of Pangea, but what it is a map of are the tectonic plate boundaries. Think of Earth's lithosphere, which is like saying crust, being made of sections or plates, kind of like a puzzle. Now you can see here, this is the North American plate. We're on a really big plate, and we're smack dab in the middle of it. We don't have much stuff going on. Now, Mr. Fickes, how much time? Okay, so we're good on time, and I'll start in then with what we learned during our plate tectonics travels. We went to 5 different locations, and I'll be highlighting those locations in the plate boundary that was there. Okay, speaking of plate boundaries, here's the motions that you can have. Push, pull, or slide. But as you look at this, as we've gone through the unit, we've added fancier vocabulary. That a push boundary is convergent, a pull is divergent, and slide we call transform. So looking at this diagram, it's showing up here in diagrams the slide, the pull, and the push, and showing some results at all of them. Okay, well here was our first stop. This one, when you see this fence, you should be thinking of a U.S. state, and that state is California. And we visited there because of the San Andreas Fault. Now this is a picture of a model that some students made of the plate tectonic situation there. And I selected this one because you see the fence that's offset, but this is on the surface. Underground, and it might be tough to see, you can see arrows pointing in different directions. This movement of plates sliding by has led to a really well-developed fault system called the San Andreas. And because you have sliding by of plates there, you have seismic activity. That's fancy for earthquakes. And when there's movement along the fault line, there are 2 main types of seismic waves that transfer that energy: body waves and surface. Surface waves head up to the surface and do the damage, where body waves stay in the earth. Then, out of body waves, there are 2 types that we abbreviated with a P and an S. P for primary, S for secondary, and we actually took big advantage of these differences in speed. P waves will always arrive at a location before S waves, unless you're right on the epicenter of a quake, then the lag time between them will be 0. So you probably remember using a method like this. But ours, this was not our example. Our earthquake was located, its epicenter in San Diego. You see here these 3 circles, and these circles are representing the distance that a quake is from Charleston, Detroit, and Minneapolis. Now, when I ask you this question, you should be thinking an answer to it. Are any of those 3 cities where the epicenter is? The answer to that is no. None of those cities are the epicenter of the quake. The circles represent the distance that the quake is from those cities. Now, another thing is the quake in the circle somewhere or on the circle? You should be thinking on the circle, and where the 3 circles meet gives you your epicenter. See, over here only 2 circles are meeting, so you know it can't be there. This is how we find the epicenter of an earthquake. Okay, now when you check out this, we've moved to another location. This location, you can see, has, well, some water, some continent, and then it's got some lava flowing out. But what I want you to take special note of are the arrows pulling away. Now, when I say this location, for our travels, you should be thinking Iceland. This is the spot of seafloor spreading. Let me go back to that just a second. In Iceland, the plates pull away, and that allows magma to come out, cool into new crust, push the old away. This is the site of seafloor spreading.